Assalamu alaikum. This presentation is on how the larynx, through its highly refined neuromuscular control and well-adapted mechanical properties, including its elastic and stiffness modulus, can adjust and finally tune the produced voice. We shall touch on an important mechanical property of the vocal folds, its stiffness and elasticity modulus, and the role played by the vocal fold muscles in voice tuning, how the vocal folds contact pattern can affect the voice quality and the vocal registers, the few laryngeal vibratory mechanisms used by us for voiced production.
All objects or structures have an inherent mechanical property that is intrinsic in the material of the object or the structure. It's the way it resists deformation, like stretching or compression, when a force is applied to it. Stress is defined as the force applied to the object to cause its deformation, either stretching or compression, divided by the surface area of the object or the structure perpendicular to the direction of the applied force. Strain quantifies the amount of the deformation, either the stretch or the compression after applying certain stress. So stress is mathematically the force over the surface area, and strain is the amount of deformation divided by the whole length. So it's a relative deformation. The ratio between stress applied to an object and strain, the result of the application of the stress, is called the Young's modulus and reflect the elasticity of the material of that object or structure. Young's module is the stress divided by the strain. Here are some examples of the elastic modulus of several materials together with their densities and the ultimate strength, which is the point at which the material would break. Large elastic modulus value would tolerate stress better and show only little strain, little compression, or little stretch when a certain stress is applied to it, compared to materials of very low elastic modulus, like polystyrene, for example, in which the small elastic modulus means that the stress can produce large strain. Stress on a rubber band would produce large strain, like maximum stretch. The same amount of stress, if applied to steel, would only produce a very small deformation, change in the length of the steel bar. In between steel and polystyrene, there are other materials, including, for example, bone, including glass, including concrete, and different other materials in between the two extremes. Generally, the greater the stress, the greater the strain. And the proportionality constant between the two, between the stress in here and the strain is there, is the Young's elastic modulus. But the relationship does not have to be linear all the time, with some increase in the stress causing a corresponding increase in the strain. The relationship can be also nonlinear, like in this graph, which shows the stress strain curve of the vocal cords. It's nonlinear because in one segment, the relationship between the stress and the strain is different from another segment. You could see here that a large amount of strain is produced by a small increase in the stress, and vice versa here, large amount of stress is required to produce only a small increase in the strain. This type of a relationship between stress and strain is therefore called nonlinear. This is a typical graph of the stress on the y-axis. Again, is the strain on the x-axis relationship for the materials of the vocal folds, demonstrating how forces, ascending magnitude of forces on the vocal fold, can cause stretching or compression of the vocal fold's heterogeneous tissues. The slope of the curve, the tangent line on the slope of the curve, quantifies the stiffness of the vocal fold, how it resists deformation. stretching or compression. The plot shows that the vocal folds exhibit three mechanical properties. The stiffness is not linear, it's a nonlinear as we have just discussed, and the strain is not equal in all directions, that's another property, and the vocal fold has also some viscoelastic behavior as we are going to discuss in the next few slides. The second mechanical property is the anisotropic stiffness. That is to say, the stiffness of the vocal fold tissue is not uniform in all directions. The stiffness is much higher in the anteroposterior direction than it is in the transverse direction. The transverse direction is much easier to move the vocal folds in the transverse direction because of the decreased stiffness compared to moving it in the anteroposterior direction. It has something to do with the anteroposterior alignment of the collagen fibers, the elastic fibers, and the muscle fibers in the anteroposterior direction. The Young modulus in the anteroposterior direction of the cover layer is more than 10 times that of the transverse plane. We know that a higher Young's modulus would mean better toleration of stress. There will be small amount of strain with a higher modulus in the anteroposterior direction than it is when the much smaller Young's modulus in the transverse direction. This anisotropic stiffness of the vocal fold has two important applications. This stiffness facilitates the medial to lateral motion of the vocal cord in the transverse direction and also helps in completing the glottal closure during phonation, as we shall see later. These are the two properties related to the non-uniform distribution of stress in the vocal fold material. The third property of the vocal fold stiffness is its viscous behavior. You can see here that the stress strain curve for loading of the vocal fold, stretching it or compressing it, is different than the graph while unloading when it is returned back to its neutral position. The stress is typically higher during the loading than it is during the unloading. This is basically due to the viscous behavior of the vocal fold material.
We now move to the role played by the vocal fold muscles in voice tuning, covering the activities of the lateral cricoarytenoides, the interarytenoides, the cricothyroides, and the thyroarytenoides, and the role played by these muscles and other factors in controlling the vocal fold's contact pattern. The direct effect of the lateral cricoarytenoides is to adduct the vocal folds by bringing them both towards the midline, helped by the interarytenoides. But they don't have much effect on the vocal fold length, and also a slight effect on the vocal fold stiffness. They only cause slight medial compression of the membranous part of the glottis and no change in the vertical thickness of the medial part of the vocal fold, the contact area of the vocal folds. This may cause incomplete glottal closure in the mid-membranous part. The indirect effect of these two muscles is to stabilize the arytenoid during its movement to adduct the vocal folds. They stabilize its position over the cricoid cartilage, helped also by the posterior cricoarytenoid, which is an abductor, but it activates during the adduction to help in the stabilization of the arytenoid cartilage. Moving now to the cricothyroides muscle. The cricothyroides is formed of two bundles. The vertical bundle is the parus recta, approximates the cricoid and the thyroid cartilage by rotation of the cricothyroid joint. The oblique bundle, the parus oblique, with fibers running upwards and backwards, on activation displaces the cricoid cartilage and on top of it the arytenoid backwards in relation to the thyroid cartilage. This would lead to a stretching of the vocal folds, increasing the length of the vocal fold and also increasing the stiffness and the tension in both the vocal fold body and also the cover layer of the vocal folds.
Activation of the cricothyroid muscle would lead to an increase in the vocal fold length by stretching the vocal folds, and also an increase in the vocal fold stiffness. These two actions would have opposite effects on the vocal fold fundamental frequency. The increase in the length would normally lead to a drop in the fundamental frequency, as shorter vocal folds would vibrate at a higher rate than longer vocal folds. But it is the increase in the vocal fold stiffness that dominates. So the net result of activation of the cricothyroid muscle on the fundamental frequency is to increase the fundamental frequency through its effect on the vocal fold stiffness.
The other important effect of the activation of the cricothyroidus muscle is through changing the vocal folds geometry. This would have its effect on the depth of the medial ends of the vocal folds, the glottal channel, and also on the fundamental frequency. The activation of the cricothyroids would reduce the thickness, the depth of the medial ends of the vocal fold. This will produce a shorter glottic channel with a shorter phase difference between the inferior and the superior parts of the medial ends of the vocal folds. It would make it easier for the subglottic pressure to open up the glottis because it's now thinned out. This will produce a higher vibratory frequency, a very short closed phase, consequently a much longer open phase. This will produce the falsetto-like voice production, falsetto register, mainly because of the shortened phase of closure of the vocal folds, the shortened depth of the medial ends of the vocal folds that would produce a sinusoidal type of waves, very high fundamental frequency, and limited number of harmonics. And now the thyroarytenoidus muscle, which forms the bulk of the vocal fold. When activated, the thyroarytenoidus muscle will induce a whole body rotation in the axial plane and the horizontal plane around the axis of attachment to the thyroid and the arytenoid. The whole of the muscle would rotate medially, and this will close up completely the membranous part of the glottis. It would leave the posterior part of the glottis open. To close up the glottis completely, you would need the activation not only of the thyroarytenoidus, but also the lateral cricoarytenoid and the interarytenoid, which would close up the remaining posterior part of the glottis.
The effect of the thyroarytenoidus muscle, the vocalis muscle, on the vocal fold fundamental frequency is a little bit more complex. The thyroarytenoidus muscle tends to stiffen and tense the vocalis muscle itself, the body layer of the vocal fold tissues, the core layer. But at the same time, it shortens the vocal fold length, and this would lead to a decrease in the stiffness of the cover layer of the vocal fold. So there will be an increase in the stiffness of the core layer of the vocal fold and a decrease in the stiffness of the cover layer. This change in the body cover stiffness ratio was noted to increase the duration of the glottal closure and also increase the vocal fold frequency. On the other hand, depending on the depth of the body layer involved in the vibration, the increase in the thyroarytenoidus activation can either increase or decrease the vocal fold fundamental frequency, as we shall see now. The final effect of activation of the thyroarytenoidus muscle on the vocal fold fundamental frequency can vary depending on several specific vocal cord conditions. We'll go through three of these conditions. And the first two specific conditions, they relate to the condition of the vocal fold length. If the vocal fold is elongated, as is often the case during phonation, then activation of the thyroarytenoidus muscle would lead to a decrease in the vocal fold fundamental frequency, a drop in the F0. But if the vocal folds are only slightly increased or slightly compressed, then activation of the thyroarytenoidus muscle would actually increase the fundamental frequency. The other factor is the effect of the activation of the thyroarytenoidus on the vertical depth of the medial edge of the vocal fold during phonation. it would tend to increase the vertical depth of the vocal fold, and also it will produce more medial compression between the vocal folds during their contact. So both these factors, the increase in the vertical depth and the medial compression of the two vocal folds medial ends, would tend to increase the extent and the duration of the vocal fold contact during the vibratory cycle, and both these factors would lead to an increase in the fundamental frequency. So the final effect of thyroarytenoids on the vocal fold fundamental frequency would vary. Sometimes it would increase, sometimes it would decrease the fundamental frequency depending on the vocal fold specific conditions.
So with any weakness or delay in the action of these three muscles, the lateral cricoarytenoid, the interarytenoid, or the thyroarytenoids, there will be a longer open phase of the glottis during the vibratory cycle. The glottis would remain open a bit longer than it should in the vibratory cycle. Normally, the open phase should be 0.40% to 70% of the vibratory cycle. If it is more than 70%, the ratio between the open phase and the total time of the vibratory cycle is more than 0.7. Then this would lead to a short contact period between the vocal folds and would allow a rapid airflow through the weakened adduction, and this would cause a turbulence. In more severe cases, when there is sufficient separation of the two vocal folds away from each other during phonation, the coupling between the two vocal folds to produce a single fundamental frequency may be weakened, and each vocal fold may vibrate at a different fundamental frequency, leading to biphonation, or a voice containing two distinct fundamental frequencies. We have noticed how a weak or a delay activation of the thyroarytenoidus muscle can produce a long open phase of the glottic cycle with a longer glottal open quotient, more than 70%. On the opposite, if the thyroarytenoidus is overactivated, it can produce a tighter vocal fold approximation during phonation and a shorter open phase. The glottal open quotient would be less than 0.4. The open phase in relation to the total duration of the cycle would be less than 40%. This would give rise to a pressed voice rather than the breathy voice if the open phase is longer. The pressed voice is often characteristic by a second harmonic that is stronger than the first harmonic. The H1 minus H2 would be negative, and this would produce a pressed voice. Somewhere between these two extremes of a breathy voice and a pressed voice is the modal voice, or the modal register, which is more commonly used in phonation, characterized by regular vibratory cycles and a rapid closure of the vocal fold with a more gradual opening of the vocal fold. The opening phase of the glottis would be between 40 to 70% of the glottal cycle. The rapid closure of the vocal folds would produce a harmonically rich voice. This modal voice is produced by the activation of the lateral cricoarytenoid, the interarytenoid, and the thyroarytenoid muscles. They would produce a large medial surface thickness and good contact between the vocal fold medial edges, and probably low anteroposterior stiffness of the vocal folds. This would produce a large vertical phase difference between the medial ends of the vocal folds, an appropriately sized closure quotient or open quotient of the glottis, and a small flow rate and strong harmonics. So what are the factors that this vocal fold contact pattern depends on? Primarily the degree of the vocal fold approximation by the adductors, the glottal channel geometry, its extent, its depth, and the duration of the contact, the subglottic pressure, and the vocal fold's intrinsic stiffness during adduction. Changes in any of these parameters can influence the fundamental frequency by affecting the vocal fold contact mode.
the vocal fold depth, particularly of the medial ends, and the contact mode of these medial ends can modulate the vocal fold vibration frequency, the F0. This F0 can be increased by the increase of the extent and the duration of the vocal folds contact, and also by increasing the depth of the contact, the depth of the medial ends of the adducted vocal folds. When the medial ends of the adducted vocal folds are thin, they can be easily pushed apart by the subglottal pressure. As a result, the glottis may never completely closes during vibration, producing a weak and breathy voice. On the other hand, increasing the vertical thickness of the medial ends of the vocal folds during phonation provides a better closure that can resist the glottis opening effect of the subglottal pressure. Also, increasing the thickness would increase the phase difference in the phase between the inferior part and the superior parts of the medial ends of the vocal folds, and this would produce a longer closed phase of the vibratory cycle. Because of this nonlinearity in the vocal folds stiffness, the increase in the high subglottic pressure can actually increase the vocal fold stiffness. The increased vibration amplitude driven by the high subglottic pressure would lead to an increase in the stiffness of the vocal folds and also the fundamental frequency. So this combined effect of the contact mode of the vocal folds and the nonlinearity of the vocal fold stiffness can lead to an increase of about 40 Hz in the fundamental frequency if the subglottic pressure is increased. There's a very wide variety of laryngeal patterns or mechanisms a human larynx can use to produce a very wide range of fundamental frequencies for certain periods of time. In reality, a certain individual would only choose to use or employ few patterns or styles or mechanisms for laryngeal adjustments by distribution of the tension and the geometry of the larynx. These are called the vocal registers, laryngeal vibratory mechanisms. So here are common examples of different ways a larynx can adopt to produce a certain required frequency. And the same larynx can choose to have this mechanism, the M1 mechanism, to produce lower frequency, or shift to another mechanism to produce higher frequencies. In the first mechanism, you can see that the vocal folds have a full body vibration. The lower lips of the medial ends meet first in the midline, followed by the upper ends, and they remain closed in the midline for a certain amount of period. The closed phase of the cycle is much longer than the closed phase of the cycle for the other mechanism, in which the vocal folds are stretched in the anteroposterior direction. They have a very short closed phase. Only the edges of the vocal fold can meet in the midline and vibrate, and they produce a higher frequency compared to the first mechanism. So a certain way a larynx can choose to produce a certain frequency is called a register or a laryngeal vibratory mechanism. These registers or laryngeal vibratory mechanisms have three characteristics. They have a certain vibratory pattern, a certain pattern of the vocal folds that is different from other registers. They also cover a certain range of fundamental frequencies and produce a certain type of sound. These are the ways you can differentiate between a certain register or a certain laryngeal vibratory mechanism from the other. The way the vocal registers or the laryngeal vibratory mechanisms are classified is rather confusing because there is not much general agreement about how many registers are there and the exact description of each of them. This is a common way of classifying the vocal registers, starting with the register at the lower end of the fundamental frequencies, the pulse register. This register, this configuration of the larynx, produces the lowest range of vocal frequencies. It has other names like a vocal fry or a glottal fry or a creaky voice.
The vibratory pattern of the vocal folds here produces a rather long closed phase of vibration, and the fundamental frequency produced would be less than 70 hertz. This is 20 to 60 hertz. This is followed higher up the scale by the modal register, the one that we most commonly use during speaking or even singing. It's characterized by complete adduction during vibration and produces frequencies between 100 and 300 hertz. It has other names like chest or head, middle or heavy voice. The top of the range is the loft register. It has other names like falsetto. It's the highest vocal frequencies range produced by the larynx and is characterized by vibration of thin and tense vocal folds that are stretched in the anteroposterior direction and have only minimal vibration. They can produce fundamental frequencies in the range of 275 up to 1100 hertz per second. But beside this traditional way of classifying registers into three registers, the pulse, the modal, and the loft register, there are other ways of classifying the laryngeal vibratory mechanisms or vocal registers, including the classification of laryngeal vibratory mechanism into four types from M0 to M3. Whether there are 3, 4, or 5 vocal registers depend on whether you include the lower register, the vocal fry, in the pulse register, or M0 here, or whether you have it separately. And the same applies to the higher end of the scale, whether you include the whistle register, the higher voiced females, in the loft register, or have it as M3 in the other classification. So that's the basis for the confusion between the number of vocal registers. We would notice here a change in three things: change in the frequency, the configuration of the vocal fold, and the voice. You see how the frequency here has exceeded 200 something with a stretching of the anteroposterior direction of the vocal fold, and then it vibrates at a lower frequency, much lower frequency, with full vibration of the body of the vocal fold. The lower ends of the medial part of the vocal fold meet first, followed by the upper ends. And that's the idea about classifying a certain mechanism or a configuration into a register, a certain voice, a certain frequency range, and a certain configuration of the larynx. That was the pulse register, the lowest frequency range a laryngeal vibratory mechanism can produce. It has other names like a vocal fry or mechanism 0, the M0. The voice produced has very low fundamental frequencies, less than 70 hertz, and it's quite deep and thick. It sounds like, yes, it's Friday. The larynx can produce this register by lowering the level of activation of the laryngeal muscles to minimize any tension in the vocal folds and avoid any stretching of the vocal folds in the anteroposterior direction. This would leave the bulky vocal folds in opposition, in contact during the closed phase of each vibratory cycle. So you have longer closed phase and you have fewer vibratory cycle producing the low frequency. The closed larynx permits only bubbles of air to pass through the thickened vocal folds with a larger depth than usual, and this will produce the popping or very low frequency sound characteristic of this register. The sound produced can also be aharmonic or have some periods of doubling or irregularities. This is the modal register, the mechanism number 1 in laryngeal vibratory mechanisms, sometimes called the chest register as well. You can see that it covers the range of frequencies that we usually use in conversation, speech, and also in singing, anything between 100 and 300 hertz. The vocal folds meet in the midline and remain closed completely during the closing phase of the vibratory cycle,
of the vocal folds is like a triangle, and in the pulse register it's more of a square, and the approximation of the vocal fold is complete during the adduction, during the adductory cycle. And during the lower tones, the larynx is brought inferiorly by the influence of the infrahyoid muscles. Now the loft register, sometimes called falsetto, or mechanism number 2 in the laryngeal vibratory mechanisms. It covers the higher range of frequencies. It's brought about by the activation of the cricothyroid muscle that would tense the vocal folds in the anteroposterior direction and also stretches in the anteroposterior direction in length. The vocal folds would be lengthened, tensed, with very thin edges that would barely touch in the midline during adduction, giving incomplete adduction, and the subglottic pressure would be increased, and the frequency would also be significantly increased. To bring about the highest notes, the larynx would be pulled upwards with the influence of the suprahyoid muscles. The whistle register, or the flageolet, or mechanism 3, is considered by some as a separate register or a separate laryngeal vibratory mechanism, while others would consider this as just an extension of the loft register. It's the highest possible register, the highest possible frequency range produced by the human larynx. It produces a sound that have a narrow and piercing quality, much like a whistle or the upper notes of a flute. There is no clear passaggio between it and the loft register. That's why some would consider it as just an extension of the loft register. You can see the very high frequency during the production of this register. So to sum up, there are few laryngeal vibratory mechanisms that can explain the way we use our larynxes during speech and during singing. These few laryngeal vibratory mechanisms or registers are given different names by different people, but they can be classified as M0, which represents the pulse register of the vocal fry, in which the vocal folds core and cover are both loose with little tension. In mechanism number 1, which corresponds to the modal register, the vocal fold body and cover both has certain amount of tension, and they both contribute to the vibration. In mechanism number 2, which corresponds to the loft register, the vocal fold body does not vibrate, but the vocal fold cover is very tensed and would do most of the vibration. The fourth mechanism, the M3, has the whistle, the register, has the vocal folds edges very thinned and very tightly stretched, and only the cover of the vocal fold would vibrate and would give almost always incomplete vocal fold closure.
By this, we come to the end on this presentation on how the larynx, through its highly refined neuromuscular control and its well-adapted mechanical properties, can adjust and finally tune the produced voice. Assalamu alaikum.